All right, hey organic chemistry. So the last class we talked about, we were in our notes here on isomerism and configurations, and we were talking about chirality. So I'm going to make us jump to page, for this video, jump to page 7 and kind of refresh your memory of what chirality is. Chirality is this idea that I have right and left-handedness. They could be mirror images that are not superimposable. Although we could call that non-superimposable. So like my right and left hand, they can be considered mirror images, but if I put one on top of the other, they're not the same. And we know that our right and left hands do different things. Okay? So that was just our introduction to chirality. And then we jumped and we started talking about molecules a bit, and we had some definition. A chiral molecule is a molecule that will have 4 different substituents. So in order for a molecule to be chiral, there will be 4 different groups. Achiral, I'll have 2 or more of the same groups. Typically, if I have 2 hydrogens on a carbon, it's not going to be chiral. And then we call those pair of molecules that are mirror images enantiomers. So my right and left hand are technically called enantiomers. My right hand is an enantiomer of my left hand. One of my hands is chiral. This is definitely considered chiral. It's chiral because the mirror image of this is non-superimposable, and so these two will be called enantiomers. Okay? So at the end of class, we wrote down how we are going to be able to distinguish between chiral molecules. And the most important thing is this business of has 4 different substituents. So the example is 2-bromobutane. Another way to draw 2-bromobutane is like this. Okay? Butane is 4 carbons. On the second carbon, I have bromine. Just by looking at it, I wouldn't imagine it being chiral, but you have to find a carbon that has 4 different things attached to it. So starting with this bromine, don't forget that this is a carbon. There's this thing. Don't forget there's a hydrogen and then a bromine. This is 4 different groups. I could do the same thing if I had 2-chloro, 1, 2, 3, 4, 5, 6. 2-chlorohexane. We could see right here that this carbon is going to have 4 different groups. It's got this chlorine, it's got this line over here, it's got this whole thing over here, and then don't forget that there's a hydrogen. Okay, so 4 different groups makes this carbon that I just put a dot on chiral. So such a carbon we call an asymmetric carbon or chiral carbon. This type of carbon is often designated with an asterisk. An asymmetric carbon is the most common example of what we call a chirality center. They are not superimposable on their mirror images. So if I had 2-bromobutane and then I made a mirror image, I'm telling you right now that these two would be non-superimposable on each other. They're mirror images, but you're going to see that one of them will have a bromine coming towards you, and the mirror image would have the bromine going away from you. And you have to have more practice with that with model sets. So it is not that these are known as stereoisomers, and these are not the same as constitutional isomers because they are actually connected the same. On a second carbon, there is a bromine, there is a hydrogen, there is this carbon, there's that carbon. They're all connected the same way. It's just their 3D arrangement is different. So let's kind of unpack this and put this together. There are some terms here and some molecules that we're going to have to look at. This is my chiral carbon. This isn't a chiral carbon. This is just a chiral center. Because I don't have to be carbon to have a what we call a stereocenter. Okay. And then this actually is an alkene. Okay, and we're going to call this the cis alkene. And if I were to draw the trans alkene, and we're going to get to this later, here's the cis alkene, here's the trans alkene. These two have the same molecular formula. They are connected the same. Right? So this carbon has a hydrogen in CH3, 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 and they are not mirror images. All of these are going to go under the class of stereoisomers. Okay? So, to kind of organize that, we have our chiral carbon, we could have a chiral center. Both of these are known as stereocenters. Right, and that's supposed to go under the blue line. And then I could have cis and trans alkenes, and there's actually no chiral carbons, there's no stereocenters. I have the same molecular formula, and they're connected the same way, but they're not mirror images. These cis and trans to each other, and we're going to talk about this later. This is later. All of these are going to be known as stereoisomers. They're going to have some sort of stereoisomerism to them. Now, we're going to focus more on chiral carbons and chiral centers for the rest of this. So, steps for testing chirality. You could make a model. No matter how you twist and turn the models, they will never look exactly the same. So make a model, make its mirror image, and so here's the image. So you could do this with model sets, and we will do this in class with some examples together. You can make a model, make its mirror image, no matter which way you twist and turn it, and we did this in class. If I put one on top of the other, just like my right over my left hand, none of the atoms will ever align. And so I actually did this example in class. We can generalize at this point. Keep in mind that the ultimate test for chirality always whether the molecule's mirror image is the same or different. If a compound has no asymmetric carbon atom, it is achiral. If a compound has just one asymmetric carbon atom, it's chiral. If a compound has more than one asymmetric atom, it may or may not be chiral. And you're going to see that if I have two chiral carbons next to each other, so if I have like a hydrogen, Br, and then maybe a chlorine and a chlorine, internal mirror plane. These two carbons, we will eventually identify them as asymmetric. They're going to have 4 different groups, but there's an internal mirror plane. And remember from class, if any object has an internal mirror plane, it will be achiral. And so if we look at my glasses here, okay, if the lens were not in here, and I was just looking at my glasses have an internal mirror plane. If I were to fold them in half, they would look the same on the left and right. So this object would be achiral. The same thing can be said about molecules. If I can't tell and there's an internal mirror plane, it will be achiral. Think about cyclohexane by itself. Right, cyclohexane here definitely has an internal mirror plane. The left side is going to be the same as the right side. It's going to be achiral. But if I threw a methyl group on here, and I know that there's going to be a hydrogen at the bottom, now, and let's say I had to draw a bromine down here, now there's no internal mirror plane. There's no internal mirror plane, and these two are going to end up being chiral. Okay? All right. So I want to start putting this to the test and doing some examples. And so I'm going to do 1 or 2 of these examples. And then for the rest of class, or for the rest of this, I want you to finish these practice examples on your own. So it says star each asymmetric carbon in the following structures, right? So here's an example. If I have this structure, okay, I have to find an asymmetric carbon. I have to find a carbon that has 4 different substituents or groups. For this example, they already did it. Here's this carbon. It's got a hydrogen. It's got this whole business. It's got this whole business. And it's got this whole business. Those are 4 different things. It looks like they're not clean and cut separate things. Some of them are connected to each other, but they're different things or they're different substituents no matter which way you look at it. Another example is this carbon. This carbon's got this chlorine, It's got this hydrogen, it's got this business, and it's got all of this business. Okay? Another asymmetric carbon or chiral carbon is this carbon. It's got this business, if you could try and see it over all this mess. It's got an OH, it's got a CH3, and it's got an H that's over here down here. So we're going to get some practice in making sure that we could do this. You have to find a carbon or a group that has 4 different things on it. So let's look at some examples. Let's look at A. This carbon has 3 hydrogens, so this is not going to be asymmetric. It's not going to be chiral. 3 hydrogens, it has 3 of the same. Not. This carbon has 2 hydrogens. Not chiral, it has 2 of the same. This carbon has 2 hydrogens. Not chiral, not going to be the same. This carbon has 2 hydrogens. It has 2 of the same. Not going to be chiral. And then we got this bromine. That bromine only has 1 thing on it. So this has no chiral centers. No chiral carbons. So a nice little trick or tip. A carbon with 1 hydrogen may be chiral because there are 3 other things to look at. So if I had something like carbon, and then there's 1 H, and then there's like a CH3, and then maybe there's a bromine, and then there's a chlorine, this is a chiral carbon. There's 4 different things. But if I had a carbon with 1 H, and then there's a CH3 here, and then a CH3 here, and then a bromine, which, by the way, this is just propane, this is not going to be chiral. It's got 2 of the same groups. Okay, so let's try another one. Let's look at 1-pentanol, right? This carbon has 3 hydrogens. Nope. This carbon has 2 hydrogens. Nope. 2 hydrogens, 2 hydrogens, 2 hydrogens. No, I'm not going to have any chiral carbons, so no chiral carbons. And then this oxygen only has a carbon and a hydrogen. That's not 4 different groups. Now let's look at 2-pentanol, okay? So I have a carbon that has 3 hydrogens, so that's not going to be it. I have this carbon that only has 1 hydrogen, so maybe that one. I'll return to it and make sure there's nothing else. This carbon has 2 hydrogens, nothing. 2 hydrogens, nothing. 3 hydrogens, nope. If it has more than 1 hydrogen, it's not going to be chiral. So now let's look at this carbon. Does it have 4 different groups? It's got an OH group. It's got that hydrogen. It's got this 1 branch on the end here, and it's got this long branch on the end here. This has a chiral carbon, and it's the second one. I'll redraw it up here. OH. This is my chiral carbon for this compound. Okay? All right, so for the rest of these examples, I would like you to try and identify any chiral carbons. I will draw I for you and G for you. It says cis-1,2-dichlorocyclobutane. Dichloro, so that means 1,2. So I'll just do chlorine, chlorine. I'm putting them on the same side of the ring. And then trans, 1,3-dichloro. Trans, which means 1 up, 1 down. All right? And then I'll draw trans 1,2-dichloro for you. 1 up, 1 down. All right, so this is G, this is I, and this is H. Eventually, you're going to be able to know how to draw that. All right, so for all the other structures, for D, E, F, G, H, I, J, and K, identify whether you have any chiral carbons and denote that with a star. So D through K denote chiral carbon, if any, with a star. Okay? Alrighty, so this is where I'm going to leave you, organic chemistry, to try to figure out and begin to identify chiral carbons. You will get another video later, but for Monday, I just want you to continue with this and then try the practice that will be given to you in class.